But the ultimate goal with linear programming, and we'll talk about what that is you are finding the maximum and minimum values if a function has both. So we'll talk about whether or not it has both, but you're finding the maximum and minimum values of a function over a certain region. And that's where the system of inequalities comes in, is to know what the region is. So I have here where this could occur. So maximum and minimum values, that's very applicable. A common area where you're dealing with maximums and minimums is in business. So it says situations often occur in business in which a company hopes to either maximize profits or minimize costs. And then many constraints need to be considered. The constraints would be your system of inequalities. And these issues, like I said, can be addressed using systems of inequalities with linear programming. So linear programming, just so you understand what this is, it's a method for finding maximum and minimum values of a function over a given region formed by a system of inequalities. And each inequality represents some constraint. So after you graph the system, you would find the vertices of the solution set. The solution set in linear programming is called the feasible region. So if you see that terminology, feasible region is the solution of a system of inequalities. But those vertices then are substituted into the function, which allows you to determine the max or min. So the maximum and minimum are always going to occur at a vertex. So that's why that last example yesterday, and there were a couple on the assignment, had you graphing the system and finding the vertices. That's where we're starting today, and then we actually use those vertices to find the max and min. So with your feasible regions, you're either going to get a bounded region or an unbounded region. So here would be a bounded region, 3 lines, pairs of them intersecting forms a triangle. The triangle is actually the solution of the system. So in a bounded region, that's when it's enclosed, the max or min value will always occur at a vertex. And there will be both a maximum and a minimum. So in this case, there will be, I'll just put both max and min. There will be both. Versus in an unbounded region, so even if you do end up with, say, an enclosed region, you have to make sure that's actually the solution set with the shading. So if the solution set of the region or of the inequalities is unbounded, meaning it would go on forever in some direction, these have either a max or a min. Still will occur at one of the vertices. Like this unbounded region has 2 vertices. So the max or min is still there, but it has either a max or min, so it does not have both. And you have to be able to determine which one it has. Does it have a max? Does it have a min? And then what that value is. So we'll go through an example of each, just so you can understand how to work through these. So this is what they look like in example 1. It says graph the system of inequalities. So you can see the first 3 here, that's your system of inequalities. And then the bottom, the f of x, y, that is your function. So this is a function in terms of x and y. It just tells you on the other side of the equal sign you have both x and y. And then you'll name the coordinates of the vertices of the feasible region. So find the coordinates, use those to find the max and min values of the function for that region. And then leading into tomorrow, so today this is given to you. Tomorrow you would have a problem where you have to set up the system and set up the function in order to actually do this. So that's leading into tomorrow. That's how tomorrow is different. So if we look at graphing the system of inequalities, first of all, the first inequality is a compound inequality. So this actually represents 2 separate inequalities. One of them, if I read this one backwards, y is greater than or equal to -6, and the other one, y is less than or equal to -2. So I actually have 2 lines to draw with that one. And again, if they're y and there's no x, are those horizontal or vertical? Horizontal. And all of these, if you look at the symbols, all of these lines that you're drawing for this system of inequalities are all solid. So I'm going to draw a horizontal line through -6 and through -2. And I'm going to shade as I go, so I know, given the compound inequality, y is in between them. So right now I would be shading in between those horizontal lines. My next inequality, so make sure also that your inequalities as you're graphing are in slope-intercept form. My next inequality is in slope-intercept form already. So my y-intercept is +2. And my slope is -1. So I should have a decreasing line. So I would go down 1, right 1. And I know I had the rulers for you to pick up. I tend to make more points than necessary because, again, the vertices of your feasible region are going to be where your pairs of lines intersect. So I like to very easily be able to tell where those intersections are. And from here, determining which part to shade for that inequality, if I test 0, 0, I'd have 0 is less than or equal to the opposite of 0 plus 2, which is 2. And that is true. 0 is less than or equal to 2. So I'd be shading below that line towards the 0. I'm only going to shade over, though, what's already shaded. So right now it's restricted to what I colored over in orange. And then my last inequality is also already in slope-intercept form. The y-intercept is 2, and the slope is +2. So I would go up 2, right 1. But actually, because I want to see, my shaded region right now is down here, and I want to see where those intersections would be, so I'm going to go down to left 1. And if I shade for that one, if I test 0, 0, I'd have 0 is less than or equal to 2 times 0 plus 2 is going to be 2. So I get the same inequality I had for the one above, so that's also true. So shading towards 0, 0, below that line, my feasible region is this trapezoid here. All right, so once you have that, then your next step is to find the coordinates that create your feasible region. So in this case, since I have a trapezoid, there's 4 vertices. And I need to name those points. So my vertices are, one of them is -2, -2. This one, very bottom left, is -4, -6. And then I have 4, -2, +4, -2, and 8, -6. Okay, and this is an enclosed region, so I'm going to have both a maximum and a minimum. And the maximum and minimum both occur at one of your vertices. So now from here, with your function, you're substituting each of these four ordered pairs into the function to determine what the function's value is at that point. So for negative 2, I'd be finding f of -2, -2. So putting -2 in for x, -2 in for y. And that would be 6 times -2 plus 4 times -2. So I'd have -12 plus -8, so that's -20. So at -2, -2, the function has a value of -20. Okay, and I do that for the remaining 3. So if I plug in -4, -6 next, I have 6 times -4 plus 4 times -6. So -24 plus -24, which would be -48. And then plug in 4, -2. So 6 times 4 plus 4 times -2. So that would be 24 plus -8. So 16. And then the last one, 8, -6. So 6 times 8 plus 4 times -6. So that's 48 plus -24, which would be positive 24. And then from here, you look at however many function values you had. So we had 4 vertices, we have 4 function values. The largest one is the maximum, the smallest one is the minimum. So our maximum is 24, and our minimum is -48. But then here's how I'm going to write that, because again, tomorrow there's actually going to be context to it. Your x and your y are going to be representing something. So say you're looking for a maximum profit, and you could say, okay, the maximum profit is $24, and that's when, I mean, this doesn't make sense with the negatives in there, but 8 of these are sold and -6 of these are sold. So again, the values here don't make sense, but that's kind of where this is headed, is there's context, x and y represent something, and this would be a profit or maybe a cost or something like that. So I would say, or I'm going to phrase this as the maximum is at, so I'm going to put the ordered pair where it occurs. The maximum occurs at 8, -6, and then is 24. Maximum at 8, -6 is 24, and then minimum at, the ordered pair was -4, -6, and that is -48. So not only saying what the value is, but where it occurs. All right, any questions there? So graphing the system, finding the vertices, substituting them into the function to find the values, and then determining your max and your min from there. So then in the next one, same idea. We had an enclosed region, so now we're going to see, I did have an example of both. This one is going to be open to look at that. With this one, the first inequality that we have to graph, we need to get into slope-intercept form first. So I would have to subtract 3x first. So 2y is greater than or equal to -3x minus 12. And then divide everything by 2. So y is greater than or equal to -3/2x minus 6. So y-intercept is negative 6. And then slope is negative 3 over 2. So down 3, right 2, or up 3, left 2. And all of these, again, are solid for this one. Determining where to shade, again, I always go back to the original inequality to test my point. So if I test 0, 0, I'd have 2 times 0 plus 3 times 0. So 0 is greater than or equal to negative 12. That is true. So I'd be shading above that line towards 0, 0. Then y is less than or equal to 3x plus 12. Already in slope-intercept form, y-intercept is 12. So I'm going to just extend it since that's not terribly off the graph. And then I just have to be careful. Slope is positive 3. So normally I would go up 3, right 1, but I want to go down 3, left 1. So the first point that actually fits on my coordinate plane here should be at negative 1, 9. I'm going to keep making some points so I can see again where my lines intersect. And if I test 0, 0 for that one, I'd have 0 is less than or equal to 3 times 0 plus 12 is 12. So that is true. So I'm shading to the right towards the 0, 0. I'm only going to shade over the part that was already shaded. And the last one, y is greater than or equal to 3x minus 6. So y-intercept at negative 6. And that also has a slope of positive 3. So here I can go up 3, right 1. And if I test 0, 0, I get 0 is greater than or equal to 3 times 0 is 0 minus 6 is negative 6, and that is true. So my feasible region is in between those parallel lines and above the first line I drew. Okay, so this is an unbounded region. Don't get confused. This is what I often see happen is don't think that the edge of your coordinate plane is a boundary. So don't think that like the points up here would be vertices. The vertices are only where pairs of your lines intersect. So this only has 2 vertices. There's a vertex here and a vertex here. Those are the only 2. And then this is extending onwards, like up forever. So further than we can actually see on our graph. So my only 2 vertices are negative 4, 0 and 0, negative 6. Bless you. And then since it's unbounded, it either has a max or a min. It does not have both. So we have to determine which one it has. So first of all, I still substitute both of my vertices into my function to get the function values. So I'd have f of negative 4, 0 So that would be 9 times x is -4 minus 6 times y is 0. And that's -36 minus 0, so -36. And then f of 0, -6 is 9 times 0 minus 6 times -6. And that would be 0. This would become plus 36, so positive 36. Okay, and then just comparing these two values to each other, I mean, obviously one is going to be smaller, one's going to be larger. So how to determine if you have a max or min and then which one it is. So it's either negative 36 is the minimum and there's no max, or positive 36 is the maximum and there's no min. So to determine that, what you have to do is you have to check one or maybe multiple. You have to check other points that would fall in your feasible region, which could include points, since these are solid lines, it could include points that are actually on your boundary lines. But you have to test other points that are in your feasible region to see if you can get a value that would be smaller than -36, which would prove this is not a minimum because you found a smaller value, or you find a value bigger than positive 36 to prove this is not a maximum because you were able to find a bigger value. So normally you want to test an ordered pair that is farther away from your vertices, so somewhere up here. So I'm just going to put here test other points in feasible region I'll just put to determine max or min. Or if you need to write something different as a note to yourself of what to do. So could somebody just shout out another point that is in the feasible region that we could test? Perhaps something that would be farther up in this area. Braxton? 0, 9. Okay, so if I pick 0, 9, because that's in my shaded region, then I would substitute 0, 9 into my function. So f of 0, 9 would be 9 times 0 minus 6 times 9. And that would be 0 minus 54, so -54. Okay, this, if I were to have gotten a value that was in between these two numbers, then that's not helpful. But this is smaller than -36. So -54 is less than -36, which proves that there is no minimum. That the farther that this extends, the smaller the values of your function actually get. They're getting smaller and smaller. So don't look at this and say, well, this is extending upwards, so there must not be a maximum because it continues to go up. This is showing that this is extending upwards and the values of the function are actually decreasing. So this right here proves -36 is not, I'll move this up here, is not the minimum. And that means there is no minimum. So therefore, to answer this question, my maximum is 36, which occurs at 0, -6. So there's a maximum at 0, -6, and that is positive 36, and there's no minimum. Okay, questions there?